Hello, everyone. This is Allie Mastardo, Senior Association Manager of AEMA. Thank you for joining us today for the AEMA Leadership Development Team webinar, State of the Industry, Emulsion Specifications and Field Performance. We do have you all on mute for the webinar, and we'll be using the question function on the right-hand side of your screen for any questions you may have during this presentation. All questions will be answered at the end. The webinar is being recorded and will be provided via email to all registered attendees. We'll now turn the webinar over to Aaron Walker, AEMA's Leadership Development Team Committee Chair, to introduce today's speaker. Aaron?
Thanks, Allie, and hello, everyone. I first just wanted to welcome everyone to AEMA's Leadership Development Team's webinar on the current state of asphalt emulsion specifications. I hope that everyone's doing well and enjoying the first little bit of December and the slide into the holidays here. As Allie had already said, if you have any questions, please use the questions function on the side panel, and we'll do our best to answer those at the end. And with that, it'll be my pleasure to introduce our speaker, Mr. Aaron Roy. Aaron holds a bachelor's degree in chemical engineering from the University of Kentucky. He also holds an MBA from Northern Kentucky University. He spent over 5 years working at Colos's Central Laboratory in Asphalt Emulsions, Pavement Preservation, Liquid Asphalt, and Hot Mix in a technical assistance and research capacity. He has since worked almost 3 years at the Gorman Group, handling an asphalt emulsion and pavement design lab, an accredited liquid asphalt testing lab, and the field quality control department for 16 paving crews that focus on pavement maintenance and rehabilitation in this area. And with that, I will turn it over to Aaron. So Aaron, whenever you're ready.
All right, good morning or afternoon or evening, depending on where you are. I'm actually in Tucson, Arizona, and if my voice cracks during this presentation, it's not because I'm going through puberty. It's because the dry air after a couple of days gets to me, because I'm from upstate New York, so I'm used to having some water in the air. But just to start off with, we have some polling questions to kind of get a feel for who's in the audience. So yeah, I think Allie's gonna show those. I can't actually see them if you're showing them though.
Yeah, so the first one is, what is your role? Are you a contractor, asphalt emulsion supplier, agency, or a chemical supplier? And it looks like most on the webinar are asphalt emulsion suppliers. The next question is, how many years of experience do you have in the industry? 0 to 3, 3 to 5, 5 to 15, or 15 plus? It looks like we've got 57% are 15 plus, 20-ish are between 5 and 15, 6 is 3 to 5 years, and 19% is 0 to 3.
So we've got a lot of really experienced people out there.
Yeah, looks like it. All right, and then our last question is, how would you rate your knowledge of pavement preservation and recycling field techniques? Strong, decent, low, or no idea? Looks like about half is decent, followed by strong, and then 13% is low.
All right. So that's it for the polling?
Yes, that is correct.
All right, time to get started then, everyone. So like Aaron Walker said, I'm Aaron Roy from the Gorman Group. So I'm big in the pavement preservation emulsion industry, and I have a real passion for that industry. So that's mainly what I wanted to talk about today. So just to introduce the topic briefly, it's sort of a snapshot of where asphalt emulsion specifications are relative to field performance, just sort of where things are, and then where things came from, and where things are going, kind of some of the future work that is going on, and some of the future work that we may want to think about as an industry to continue to evolve everything forward. And I want to make sure that I frame this presentation not to, bash any of the current work that's going on or the work that's been done, because there's been some fantastic work done through ISA, through all the government organizations and everything to really evolve these treatments from relatively simple and poorly understood to highly engineered treatments, and emulsions themselves from, basic things to highly engineered products. So a lot of evolution has happened, but this is just sort of to give like a present state and maybe just honestly start the conversation of where we need to go, asking, because a lot of you have a lot more experience than I do, so you'll probably be a big part of taking everything to the next level with all of us together. And I think that kind of ties into what the leadership development team is all about, sort of the next wave of leadership in the emulsion industry. All right, just to give a brief outline to the presentation. First off, I'm just going to give a background and sort of touch on why this topic seemed relevant. Then I'm going to go over relatively quickly, because the goal of this is not to be another Emulsion 101. I'm going to go over some basics of emulsion, some application. Then I'm going to highlight some current specifications and sort of go through what all that means, but sort of high level, because it seems like the majority of you have a fair bit of experience. And then the crux of the presentation is going to be the feedback we got on examples that myself and various people have seen where the emulsion specifications by themselves kind of fall short for us. And then I'm going to wrap it up sort of talking about some of the really exciting future work that's going on and maybe some other future work that might need to go on. So first off, why is this relevant and why did we even mention this? So I had some of my own experiences this year and in previous years when I feel like you're trying to communicate about these products, and it's difficult to have, there's like a language barrier there if you don't want to tell somebody exactly what you're doing to get to the end result of what you're trying to achieve. There can be a little bit of a language barrier there, especially when you get into the chemistry side and some of the solvent sides. So that's sort of the impetus, and then I started talking to more and more people, and more people kind of agreed. People that know a lot more about this stuff than I do kind of agreed there are some drawbacks there. So that was kind of the starting point. But I want to kind of just tell you a story to sort of frame the narrative for you. So this is just a PowerPoint, saved images. But just imagine this is Sam. He has his own contracting company. He founded it from nothing. He used to do some paving, let's say, in another contracting company. He's built it up, and he has a passion for more preservation, recycling type treatments. So that's where he focused at in his company called Best Contracting LLC. So he built that up, does chip seal, micro, fog seal, all the recycling treatments. That's his main focus. And he's a family man and just a simple guy, and he's kind of built that business up. And then John is the owner of Super Emulsions LLC. Now this is a plant that produces a wide variety of emulsions. He's also a family man, also a relatively simple guy, and started all this up. Actually inherited the plant from his family, and he understands the emulsion, but he's not a chemist either. Neither one of these guys are chemists. They're guided by specifications and history mostly, and they have a great relationship. So Sam primarily buys all of his materials from John. They've worked together to make tweaks here and there and gotten all those materials to perform the way that Sam wants them to perform in the field and the way that John can make them. So I'll say that's a partnership made in pavement preservation heaven. And I'm sure all of you out there, whether you're contractors or supply yourself, have seen these partnerships develop where you get those materials to behave the way the contractors, whether it's even down to the crew guys, want them to behave, and then everybody's happy and everything's rolling. But what happens is suddenly John has a big problem, a fire is a little dramatic, but it seemed like the best picture to show it. But let's say for whatever reason, John can't supply Sam. Could be 100 different things. Could be COVID. So if John shut down, then he can't make material, right? And you guys all know better than I do. We have a intense industry, intense season. One day lost is a nightmare. So what can Sam do with this situation? Sam can't get emulsion from John, and there are other suppliers in the area, but he doesn't really know them. So what does he do? Because he shut down his crew guys. His crew guys aren't going to be happy about that. His customers aren't going to be happy the work's not getting done. So what does Sam do at that point? And now John and Sam are good friends. They're drinking buddies. So John probably wants to help Sam, but how can John help him? Because in order for other suppliers to truly give Sam what he's looking for, John would have to open up his formula book and tell the people what he's doing. And that would be very problematic for him coming into the future, because then all his competition would have all his secrets. And there are secrets within our industry, you know, how you make different things, how your formulas and things like that. But at the same time, John feels bad for Sam. So sort of the end result of that is, if there was a way that John could communicate more effectively with other people to give Sam the products he's looking for through, you know, more evolved specifications and things like that, it would be easier to avoid problems like this. And from my own personal experience, we've had problems like this. Now, whether it's a plant going down or it's just a logistics issue, trying to buy materials from other suppliers, they do things kind of their way, we do things kind of our way, because the specifications are just so broad that, as we'll get into, you can have a lot of different products that fit the same spec that are nothing alike. So this section I'm gonna not spend a ton of time on, since it seems like you guys have a lot of experience. This is some basics on what an emulsion is and going through some of the pavement processes. So just a brief history. Asphalt emulsions have actually been around for a fairly long time. They were originally developed as a dust control system, and then they started taking off in the middle of the century for more of those remote farm to market kind of roads, because it's difficult to have, you know, mixed plants and stuff close enough to get that work done. So, you know, things like cold mix and, you know, oil and stone or chip seal started taking off, because you can go a lot further with it just hauling the oil. And then, where some of these treatments were driven more by cutbacks, environmental restrictions started coming around, and that started driving asphalt emulsion growth, which we're still seeing to this day. And now we reach today where these products are highly engineered at this point, much more complicated than they used to be even 10, 20 years ago. Adding more polymers, more different additives, more different chemistries to make them perform better. And as these products evolve, so do the purchasing specifications need to evolve to address these products. So not going to spend a ton of time on this. This is just, what is an asphalt emulsion? Immiscible asphalt sheared into water and held there by chemistry. It's a picture of mayonnaise under a microscope that I always thought was cool. But not gonna spend a ton of time on that. We've got cationic, we got anionic. They're held in suspension. This is just a picture of, you know, they gain their charge, and then we have a negatively charged aggregate particle. So that's I think important to understand that part of the functionality of the emulsion chemistry, it's its ability to adhere to stone in some of the treatments we'll talk about. But not gonna spend a ton of time on that either. So this is what emulsion's functionality, which is very, I think, a key point to understand with what we're going to talk about in some of these tests. So you have a stable emulsion, and then the material can flocculate together, so the particles start coming closer, and then they reach a state of coalescence, which at that point a lot of the water is out. It would be called, you know, set or broken, but it's not fully cured. That takes a period of time, which can vary on climate, can vary on asphalt, can vary on chemistry, can vary on how much water did you put in the system, how much water was already in the system. Does it rain every, you know, 1,000 different things can impact that. And that's a very important piece to understand, because the final strength of some of these products isn't reached until you fully set and cured the product. This is just to go over naming briefly, so that when I start rattling off different names, we don't get confused. So the first piece of the naming convention is based on the charge, like we talked about briefly on the aggregate particle slide. So if it's positively charged, it's called a cationic emulsion. If it's negatively charged, it's called an anionic, and if it has no charge, it's called a non-ionic. And for naming conventions, anionic just doesn't have a letter, and cationic has a C. So, for example, CRS2 and RS2 would be cationic and anionic versions of otherwise the same material. Then we have the high float versus non-high float, which is dealing with the coating thickness and the gel formation, which is a test we'll touch on later. And then there's the speed at which the emulsion sets. So we go from rapid, medium, slow to quick set. So quick set's kind of a micro term, and then rapid set obviously is the fastest, medium's right in the middle, and slow set's obviously the slowest. So rapid sets are a lot of your surface treatment, chip seals and things like that. Sometimes tack coats can get in there. Medium set is a lot of your mixed grade, and then slow set and medium set can be your recycling speeds. And then the number indicates, the 1 indicates a low viscosity range, and the 2 indicates a higher viscosity range. And then if there's an H in there, that's for hard base, probably 6422 in most areas, or probably under 100 pen. And then S indicates a soft base, probably 5828, 5228, or over 100 pen, or 150 pen. Depends on where you are. Typically for the soft, you actually have to be probably over 150. So that's an extra soft kind of material. And then depending on where you are, the addition of polymers and latex can have all kinds of different letters. Some places call it, for example, a CRS2P. Some places call it CRS2L. I've not really seen S, but that was on Road Resources slide, so here it is. But that's just indicating that the presence of polymer to achieve that, whether it's chip retention or extra strength, depending on the process we're talking about. And then this slide is very important. So this is kind of why we do what we do when it comes to maintenance and rehabilitation. So I'm sure you've all seen this before, but we're looking at pavement rating. So you put down a fresh hot mix. We're up there at excellent condition, hopefully, if the hot mix contractor did a good job. But then over time, it starts to deteriorate. And that's a process, of oxidation, traffic, everything that's making that pavement drive towards failure. So the argument of preservation is to bump it up a little bit. You're not necessarily going to get it back up to A, but you're going to get it a little higher and buy yourself some more time before you get to that dreaded complaint line. So we'll call the complaint line the point at which it goes from okay to, well, we really need to do something about this road. And also, if you look, all the preservation treatments fall above the complaint line, and the rehabilitation treatments fall below the complaint line. So just going through them quick, kind of in order of strength, we'll call it: fog seal, chip seal, micro slurry, combination of both, and an ultra thin overlay. These are what I would consider the main preservation treatments. And then rehabilitation, so once the road is too far gone just to surface treat, the hot in place recycling, cold in place recycling, and full depth reclamation. So just to go in a little more detail on those above the complaint line. So fog seal is just, it's exactly what it sounds like. You just take some asphalt emulsion, typically diluted, spraying a very tiny application rate to sort of give yourself a surface of asphalt, because the asphalt from the original hot mix is probably worn off, oxidized, and just hoping to buy yourself a little bit of water penetration prevention. That's really all you're buying yourself. But you want to be careful with fog seals due to a loss of skid if you overdo it, which is why they tend to underdo it and have a very tiny application rate. Then chip seal, which I'm sure you're all familiar with wherever you are, stone and oil, as people call it around New York, is just, you spray asphalt emulsion, then immediately follow it up with, whether they're 1/4 inch, 3/8 inch, or whatever stone, all of a, generally speaking, uniform size. And that's just to seal the surface, similar to a fog seal, but also buy yourself some skid resistance in addition to that, and some extra strength, because those aggregates will help protect that sealing course. And then micro surfacing is a very thin lift application, which is mixed in place with the oil, the stone, the cement, and potentially some other additives to put down maybe 20 or 30 pounds per square yard. And that's similar to chip seal to preserve the surface. Some of the advantages of micro is the surface texture that you get is much more fine, which some people prefer, and it can potentially handle higher volume, higher traffic roads. This was actually developed in Germany on the Autobahn. And then this thing has a million different names. When it first came out, it was called NovaChip, but I think that's not a thing anymore. We call it pave replace surface treatment. Some of other states we work in call it ultra thin bonded wearing course. So this is basically, it's a hot mix chip seal So you have a gap graded layer of hot mix, less than probably 80 pounds, and then you put it down with a spray paver. So you have a high application rate of a CRS-1P grade emulsion, and you put that down, and it's supposed to wick up and hold the hot mix in place. But it's a preservation treatment. Sometimes it gets extended a little far, but it's really a preservation treatment. Just falls in line with these, so it's kind of like a hot mix chip seal, as I said. And then below the complaint line, you have the rehabilitation treatments. So cold in place recycling, you go in, you mill out, 3 to 4 inches of the pavement that you have there, and you might add some stone, you might add some cement, and you mix it with some emulsion, you put it back in place, and you have yourself a new road. Hot in place is similar with the heater scarification. They go down a little bit less, and then reprofile everything, and they actually include a rejuvenating component, so they rejuvenate what was there along with the heater scarification to bring the asphalt binder that's inside of the mat back to similar how it used to be. And then cold mix paving, which is kind of something we do a lot of in the Northeast. Some places don't do as much of it. Is just what it sounds like, paving with emulsion instead of paving with a hot mix. So for that, you're doing potentially full lifts, or we do a lot of like 1/2 inch, 1/4 inch stone mixed together as like more of a surface course kind of level, but you can do up to like 3 inches. We pave with crusher run and all kinds of stuff. And for that, use kind of a medium set, so you have the correct workability to get it through the pug mill, or we actually have a Midland mix paver and get it down. And then full depth reclamation is taking the entire, up to like 6 inches and restabilizing everything, making it homogeneous and leveling it off. All right, now I'm going to talk a little bit about emulsion specifications in some more detail. Really, it kind of breaks down into 2 domains when you're talking about an emulsion spec. There's the physiochemical properties of the asphalt emulsion itself, and then there's the physiochemical properties of the emulsion residue. So these are 2 very, very separate pieces of the puzzle, because the residue properties, that's going to be how it behaves once it is fully cured in the field, theoretically. The emulsion properties is how it's going to behave in your plant, in your truck, and all the way to the field, and in the field for that first, whatever time it takes to cure, for that first week, because that's all ties back to the chemistry and the behavior of the asphalt emulsion itself, because you don't achieve the true residue properties until it's fully broken. So just going quickly through some of the tests that are in the 2 domains. So for the emulsion side, we got viscosity, demolisability, cement mixing, particle charge, sieve, and storage stability. For the residue side, we got pen, ductility, elastic recovery, solubility, float, and softening point. And then kind of bridging those 2 together is getting residue content, which is a test in itself, to take you from the emulsion to the finished residue behavior. So just going through some of the tests, sort of high level, and I threw the ASTM and AASHTOs on all these in case anybody wanted those for reference. So this is to determine the viscosity. If you remember back, that was the 1 or the 2 on the emulsion name. So this is the material's resistance to flow. So thinking about a chip seal, this is, you spray it out on the ground. If it's really thin, what's it going to do? It's going to run off the side of the road. If it's really thick, you're going to get cornrows down the road. So it's finding that balance in how the material handles, how the material pumps, and then on your mixing grades, it matters because of how the material is mixing in the box and various things like that. You want it to be workable, you want it to be flowable, you want it to behave the way that you want it to behave. It's also true of tack coats, and especially fog seals. You have to have that lower viscosity in order for it to be able to fog out and get your application rate that you're looking for. If you try to do that low application rate with a thick chip seal, it wouldn't work out for you, and it definitely wouldn't go through the nozzles that you're trying to use for that. The next test I'm going to talk about is demolisability. So this is a test that you take the asphalt emulsion, you react it with either dioctyl sodium sulfosuccinate or calcium chloride, depending if it's cationic or anionic. Now, and there is major problems with this test, which we'll touch on later with some of the expert responses, but it's designed as a chemical reaction. So but really the goal is to see how the material responds environmentally. Also, the chemical reactions were derived from specific chemistries when these tests were developed, and our industry has evolved a great deal since then. So for some of the chemistries out there, they don't correlate well with field correlation, with field results and what you see in the field. And they actually kind of limit the potential of some, new ideas and new evolutions. And the reactivity, the chemical reaction you're generating isn't necessarily telling you what you're going for. Because what you're going for with this test, for chip seal, for example, is how fast is that setting up to hold that stone. And I've seen, and I'm sure you've all seen, things at the bottom of the demolibility spec that set up beautifully, things at the top of the demolibility spec that don't set up beautifully. So I run into a situation where I lean more on what the guys in the field are saying than the actual spec, because it's kind of just a tangential relationship to what's really going on in the field. Like it does tell you have less chemical in there, but there's a lot of different factors that go into how it breaks in the field. And then cement mixing is the balance for the other end of the spectrum. So this is to make sure that a material is slow enough to be considered a slow set material. So you just take the emulsion, you mix it with Portland cement, and you make sure that not too much of it breaks. Now, this one is very problematic as well, because you get into situations where you're dictated by this to have something be a slow set, but for FDR and CIR, for example, you may not necessarily want it to be so slow. And there has to be some way to have a better, field relationship for the behavior we're trying to see out of these emulsions. There's also some issues that we'll bring up about fog seal and tack coat having to pass this test and then being extremely slow. It ties the other end of the spectrum, and it made sense when it was developed, but I think we need to start going to something more performance-based. And then the next test is particle charge. This is basically just to see if something's cationic or anionic. Cationic and anionic come from cathode and anode, and it's to sort of see the charge of the particles to tie back to the affinity for the aggregate, but it's problematic at best. You're generally better off if you have the ability to check zeta potential doing that, or just grabbing some aggregate and seeing how it mixes together and seeing its affinity, because the test itself is problematic. So this is more of a handling test, but it's important to make sure there's not too much shot being generated in the material. It's just you put it through a screen and see how much shot you have, and it's got to be under a certain amount. But the interesting question is this, which we'll bring up later, is what if you have some but not over the spec? Isn't that an indicator that there's a problem with the emulsion? And if you're driving so far that you have none, by chemistry, are you impacting other areas? Because in the end of the day, the main thing we're trying to avoid is plugged nozzles. So we're not having a huge problem with that. Like, let's say the job is going off beautiful, and then 2 months later we see that, oh, we were barely over the sieve spec. I mean, is that really relevant? This is another handling kind of test. So this is the storage instability test. It's a relatively simple test. You just fill this cylinder up, and you take out the top portion and the bottom portion, see how much residue's in there to see how much of the asphalt has settled out in the material. So this is the two different methods to get that residue back from the asphalt emulsion. So the one that we use typically to do the testing on is the distillation test. So you just load up the still, put it through a condenser, and heat it up to either 350 or 500 degrees, depending on if it's got polymer or not. But ask yourself, when's the last time a road that was being done a cold technique on got to 500 degrees? It's far excessive of anything these materials ever see in reality. It has an impact, as we're seeing more and more as the performance grading system for hot mix evolves. It has an impact to oxidize and age these these materials. And work is currently being done, which we'll talk about later, on improving this recovery method. But a lot of the properties that are being focused on and have been focused on come from these recovery methods. So it's important to understand the impact that they have. And also, all that we talked about with chemistry and demulsibility and how it's setting up, when we're heating something to 500 degrees and holding it for 15 minutes, that's fully cured. There's not 1 ounce of water left in that material at that point. That's the point of the test. But the failure modalities of a lot of these processes can happen during that window where things aren't necessarily fully cured, bad time of the season, rainy day, or bad situation. So when you're looking at the rheological performance of the residue, that doesn't at all address the chemical impact. So I just wanted to go over at a high level some of the residue tests. So we have penetration. I'm sure you've all seen it. You just stick it with a needle, see how far down it goes. If it goes down less far, you have a lower number. It means it's a harder material. You have ductility, which you just stretch the asphalt until it breaks. You have elastic recovery, where you stretch it a certain amount, cut it, and see how much it recovers. You have the float test, which is mainly used for the high float gel materials we talked about earlier. It's just you fill that little doohickey up with asphalt, put it in a heated water bath, and see if it floats long enough. And then softening point, which kind of correlates back to float test, is really, we only use it in New York for micro. It's used sporadically. It's fairly popular still in the roofing industry. It was popular in the paving industry in the past. It's just you take 2 balls and you heat the material up until that asphalt flows to the point that it hits the bottom, and that temperature is considered the softening point of that material. So it's the material, it's the point at which it's flowable, basically. So this is just a typical spec. So I've highlighted here a CRS2P, and this is New York's. And I just got this from Asphalt Institute. So just running down the tests, that viscosity range, you've got 100 to 400. Now I just want to highlight how huge that range is. If you've handled these materials and you handle something at 380 and something at 120, those are not the same material. Like even pouring them or playing with them, one's SERP and one's, I don't know, not quite water, but pretty thin. Storage stability and sieve have maximums that you're allowed. Particle charge is on there as a positive. You got a demulsibility minimum that you have to meet. You have a minimum residue content, maximum oil content, classification tests, and then you have various ranges on the penetration. So looking at the penetration, it's a pretty big range. Ductility, as the test pretty much always passes. You have a minimum elastic recovery that is there just to make sure you're putting latex in it or polymer modifying the asphalt. And then you have a solubility and TCE requirement. So I'm not going to run through them all for this, but I wanted to highlight CSS1H, and I wanted to highlight specifically that viscosity range of 20 to 100 and that 57% minimum residue content, because we'll come back to that. But and as we mentioned, 40 to 90 is about the H range for penetration. And then one more I wanted to highlight quick is HFMS2. So it's got, again, the big viscosity range and the typical requirements, and then an 8 max on oil distillate, and then a huge penetration range, 100 to 250. All right, this is the crux of the presentation where I wanted to spend the most time. So when I first brought this idea up with the leadership development team, my thought was I didn't want it to just be me up on a soapbox. So I wanted to get feedback from lots of other people. So the first thing we did, we sent out a survey to all the leadership development team and got a ton of great feedback on what they've seen. And then we sent out a similar survey to the AEMA expert technical response committee and got some feedback from the expert group as well. So the first thing I'm going to go through is some of the responses that we saw from our leadership development team. And then I'm going to go through some of the responses we saw from the experts. So first I'll touch on my own experience. So I've had some difficulty, whether it's, having plant problems or, logistically that you're closer to another plant. It's hard talking technical guy to technical guy about, because they'll just say, well, what do you want? Well, as you saw some of those specs like an HFMS2, the range is enormous. You could drive like 10 semis through it. So you can specify exactly what you want, but to truly get what you want, you have to start getting into formulations. You know, what chemical do you use? What amount of chemical do you use? What solvents do you use? You know, what residue do you target? Things like that, which are ultimately proprietary, so you don't want to tell that to other people. So you end up just having to settle on their version of it, which then your guys in the field, all of a sudden something's different and they don't like that. And then I've also seen some examples where specifications which drive everything ultimately for a DOT were adopted for different treatments, and then the naming methodology alone caused the wrong material to be utilized in a project. All right, just going over some of the responses. The main response we got back for Tack coat, and I didn't really mention Tack coat in the preservation because it's an interlayer treatment to hold different layers together, but it is a major mover for most asphalt emulsion suppliers. The specs don't really address the field concerns, like the need for preparation, the need for proper application rate, and the setup speed of the material. So a typical Tack coat might be a CSS 1H. And as we mentioned, the cement mixing test dictates that that material is very slow. But there can be problems with that, especially if you have certain climates, certain times of year, where that's not setting up fast enough for your paving operation to be successful, where they end up driving through it and smearing it all over the place. And that's some of what some of these newer high performance Tack coats are trying to address. But and also the point was brought up as a separate point that the residue needs to not only vary by the climate. You know, you got one area you might need to use 5828, another area you might need to use 6422. You go somewhere else, you might even need to use a 40 pen. And it all should vary by climate, but it should also vary by time of year. You need this to be such that if you drive over it, it's not necessarily extremely tacky. There are also less tracking Tack coats out there, but they have problems in the colder climates with debonding issues that were brought up by some of the people of the leadership development team. And a separate topic was the high performing Tack coats. It was brought up that many states don't capture the benefit of these materials. So only certain states do bond strength or anything like that. And it's very difficult to get these products approved because they don't really address or test for the benefits. So why would they pay for extra performance? And it was also brought up that some of these materials may have even more issues with climate, humidity, shade, temperature, because they're a little more engineered. So they're a little trickier to handle, we'll say, than CSS 1Hs or what have you. Fog seal, the response we got was that the reactivity varies widely and does not perform well in colder months. So you'll typically see that fog seal can be problematic in setting up in the two tail ends of the season, at least up in the Northeast where we are, given the same formulation. But that formulation is dictated again by the cement mixing test, that it has to be slow enough to pass that. It's also dictated, especially with fog seal, they have to dilute it and they tend to beat it up pretty substantially, but it hurts you on the other end if this material doesn't set up properly, because you tend to open it to traffic pretty fast, and it might necessitate the addition of sand to give you that skid properties and keep everything safe. Here's some of the responses we got from chip seal. One we got multiple times with the agency specifications are too broad. So, you know, like we looked at, that 100 to 400 viscosity is very broad for this material. I mean, a lot of people probably wouldn't want something at 120, but if you just go and buy CRS2P and it's at 120 viscosity, well, you got in-spec material, so what are you going to do? People have noted they've had situations where the viscosity while in spec was too low for hill situations. People have noticed that the spec in no way addresses chip retention or crack reduction, and that chip seal really needs to start looking at being tested as a system. And there are tests out there, like we do the Violette test and the sweep test, but at that point you have to have the aggregate and the emulsion. So going back to Sam needing to buy material from somewhere else, then he's going to have to go get a sample and send them over there, and they're going to have to play around with it. He needs material quick. This is just an example of two different roads. So the one on the left, we'll call it flat and sunny and pretty nice picture. The one on the right is relatively hilly and shady. What if the same emulsion was applied to both of these jobs? For the one on the right, you need something faster because you're very shaded, you don't have a lot of sunlight helping you, and you also don't want something not setting up when you're on a hill like that. And you also need something thick. You probably, if you were at 120 viscosity, you'd probably have problems on a hill with that steep of a grade. Whereas the one on the left, you probably don't want it to be as fast because the sun and the open air and the ability for the air to just flow across it will drive it to break faster. But typically these would both be, whether it's CRS2P, HFRS2P, they would both be the same spec, but you would have to understand the job to understand what you need for the different situations. Some of the responses we got from microsurfacing was that the residue characteristics need to be better understood. So some of the work we're going to talk about later is attempting to address that. Micro, of course, has to be tested as a system through the mix design process, which is an excellent process. It's been developed through ISA over the years. But is there a way to better specify the chemistry so that, let's say Sam has a big micro surfacing project he's doing, and all of a sudden John's plant goes down? I mean, if he's buying it from somebody else, they're going to have to do a whole new mix design. That's 2 weeks. Is there some way to dictate the chemistry of this material so that he knows I have a limestone system or I have a granite system? This will get me pretty close. If I know my cohesions and things like that work out, this will get me pretty close. Is there a way to dictate that on purely the emulsion side? Oh, and then another issue that was brought up by someone in the leadership development team is that job site QA for micro is a big issue, making field adjustments based on the initial lab mix design and the emulsion and things like that. For NovaChip, or whatever you want to call it, the emulsion viscosity can be problematic. And although it's dictated as a relatively wide range, you actually want it to be a very narrow range because it's very easy for it to be too thick or too thin. Too thick, the small nozzles and spray paper will give you problems. Too thin, it will run out of the mat on you. Emulsion reactivity can also be problematic, especially at the tail ends of the year. So the specification with Demolisability and everything leaves some to be desired when it comes to truly setting up as fast as it should and adhering to that bottom surface when that bottom surface is tending towards colder. And the residue properties in the finished emulsion need to better address the desired performance of the complete system. Cold mix paving, the emulsion specification doesn't tell you anything about workability, compatibility, or coating. Generally speaking, people that do cold mix have to do it in-house and have to make the emulsion themselves, because trying to communicate to anybody else, they would have to get your stone, they would have to do lab testing, they would have to go through it. And also, what are the appropriate residue characteristics? If you're putting more solvent in order to get better workability, you're impacting your end residue properties. But as you saw back on the slide, HFMS2 has a massive residue range. And then the another point is, what solvent are you using? How much solvent are you using? As you saw in the spec for HFMS2, you're allowed to use up to 8%. So what is the best? And what is a way to specify that so that Sam could just go to another emulsion supplier and keep his cold mix crew going with his stones based on the work he's already done? And it's also critical to the chemical break speed of the material relative to the stone, and understanding that. And how does he get that from somebody else? Because CMS is right in the middle of the range. And how does he get that from somebody else without just telling them what he's doing? He would have to give them his stone, and it would probably take them weeks, just like micro, to figure out what loading level he really needs for his particular project and his goals. Cold in place recycling. The emulsion specifications don't really address the cure time of the finished mat. There are some mix design tests in terms of raveling and different things like that that may get there, but the emulsion specifications by themselves don't get there. A note from the LDT, the lab mix design needs to be performing the actual pavement and additives that you're using is very critical, and the residue properties are not properly understood in terms of their impact on finished mix performance, because you can have the same job and do a CSS1H or an HFMS2, and if you remember back to the specifications, residue-wise, those are very different materials, especially with the allowance of up to 8% solvent in the HFMS2. So touching on the HFMS2, this is a major point. So this same product, I mean, we're a relatively small company, and we have 5 different versions of it. You can use this for cold mix, tack coat. You can use it for cold in place recycling. You can use it for cold central plant, probably FDR too, and it's all called HFMS2, but it could all potentially be very different materials in terms of function and performance. It could even be different in terms of chemistry, different in terms of solvent content, and all kinds of different things. So what if Sam goes and buys cold mix from a company that only does recycling? Like all they do is recycling. So the workability needed for virgin aggregate cold mix, they've not really thought about it, or vice versa. Full depth reclamation. The emulsion spec is often confused with tack coat, so we'll touch on that a little bit more. It's 65% versus 57% residual. The plasticity of the subbase can be a huge problem for FDR, and if you need the chemistry to get beyond that, you really have to be able to address that. You need your chemical system to work for you, and there's nothing in the CSS1H specification that really drives that. Little work is being done on the effects of rheology and the impact of it on the stabilization effect on the FDR. This is just highlighting the CSS1H point. So CSS1H, as written in the spec that I highlighted earlier with the 57% residue, that's tack coat, right? That's fog seal, tack coat, or tack coat. And the same material called CSS1H is used for reclamation and cold in place recycling. And for that, typically, it's done at 65% residue and with an engineered chemical system, much more complex than your typical tack coat CSS1H. But looking at those two as they're listed on my slide, if you were talking about them, they're the same thing. And if you're dealing with bidding, something with 8% less asphalt is going to be cheaper automatically, and it is going to have an impact on how your end product performs. If you did a mix design based on CSS1H engineered and you end up with CSS1H fog seal, which has happened because a lot of the times the CSS1H spec will be copy pasted and you'll end up with that 57% residue in there. And if you try to do FDR jobs with that tack coat chemistry, they won't set up the way that you want them to, and that can be very problematic. All right, here now going into some of the expert responses. The first one is more on the chemistry side of things. They mentioned that CRS, demulsibility, and cement mixing are totally divorced from the field and developed with very specific emulsifiers in mind. So we touched on this when we talked about the spec. It's a specific chemical, so it's a specific chemical reaction. So it's important to understand that that test doesn't necessarily tie to field performance. They also mentioned that residues need PG grading and that particle charge should probably be replaced by either zeta potential or actual adhesion testing. The next one was on asphalt issues. They mentioned that ductility rarely fails. PG will simplify this. Cement mixing, there needs to be a way to categorize slow setting emulsion based on actual field performance and not an arbitrary mix it with Portland cement test. Some general issues: emulsion tests versus residue tests. The rheology of the residue alone misses part of the picture, and we need to do more work on looking at the emulsion itself. And this was also mentioned that Canada has had, and the northern US has had a disconnect between residue and viscosity ranges. Where they'll have a minimum residue, and reaching that minimum residue necessitates that you exceed the maximum viscosity, and that's been problematic in some of the specifications with people not having full knowledge. And then someone else brought up that which we'll touch on in a minute, the Emulsion Task Force is working on developing performance-based specifications for emulsion, focusing on the residue and residue recovery, and the residue needs to be PG graded. And a final point from one of the experts is that the sieve specification may be problematic for microsurfacing because while it may pass, if it is generating some sieve, this could be problematic during pumping, clogging up screens, and lowering the final residual asphalt that you get into the microsurfacing mix, which will impact the performance based on the mix design you did in the lab. All right, now we're going to talk a little bit quickly about some of the future work that's being done. So NCHRP 963 is a calibrated and validated national performance related specification for emulsified asphalt binder. So very smart people, much smarter than me, are working on this, like Mike Anderson and NCAT and various people like that. So phase one, which has been completed, was a literature review, a look at a preliminary specification and coming up with a plan for phase two. Phase two is where they're actually at right now. So they're doing some field projects and testing the emulsions with the new proposed protocol. So first I wanted to touch on the proposed new recovery methods. One of them is ASTM D7944, which is a vacuum oven recovery for 2 hours at 60 C. So the vacuum helps drive out the moisture without overaging the material because you're only at 60 C, not 200, whatever it translates to Celsius, 260 C or something like that. And AASHTO R78 procedure A is recovering. It's on a glass 24 hours ambient and 24 hours 60 C. And then AASHTO R78 procedure B, which seems to be the favorite child from what I can tell. It's recovering residue using low temperature with a thin film on a silicone mat. So it's about 6 hours. So it kind of makes sense, you know, just with lab work, you put it in first thing, it's take it out at the end of the day. You have some material, might have some time to do some testing. So all of that testing is going to be done using a dynamic shear rheometer. And I don't know how familiar everyone is with that, but this is taken straight from the PG grading system used for hot mix binder. So it's just two plates that come together with a little puck of asphalt that you trim to a nice shape. It turns a little bit, gives a little bit of stress, measures the strain, and that stress over strain tells you the modulus of the material. You measure the modulus over time and get things like the phase angle, and then you ultimately determine how that material is responding to stress and strain, and that correlates back to field performance of the finished product. So this is an example proposed residue spec for a chip seal. First thing I want to highlight is the surface design, high temperature and low temperature. So this is exactly like a PG grading system. So you got 55, 61, and 67, less than that, and then various low temperatures that they're greater than. So we're trying to determine a true emulsion performance grade criteria using the various rheology testing from the DSR. So there was also a field trial component. We had 2 chip seals and 1 micro that I know about in New York. There were 13 total as of May of this year. I just talked to Greg Harder, who's running that, and he said he did 1 more this year, so that's going up to 14. And they were chip seal, micro, and slurry seal. And he took asphalt emulsion samples from the job. He also was at the job and took field samples, at least for our micro project he did, and did a ton of testing back at AI to see how that residue compared with the new testing protocol based on specifications. And now he's also taking a look at how the finished product in the field is performing over time to tie that back to this residue testing. So it's clear, going back to our 2-domain situation, that's a lot of work by some very smart people is being done to address the emulsion residue physicochemical properties, as well as the residue recovery method and some problems there. But there doesn't seem to be a ton of work going on in addressing the physicochemical properties of the asphalt emulsion itself. So how it performs from the moment it's made until the time that it fully cures in the field is not being addressed as much. And it seems to be, and a lot of people that know a lot more than me seem to agree, that that's something that needs to continue to evolve in order for our industry to continue to evolve. So just wrapping up, residue's only half the battle. Is there any work out there to address curing, setting, and coalescence? Is there any work out there to improve the understanding of handling? Is there any work out there to better tie the material to the process? Just wrapping up, that's the goal of this presentation, is just to pose the question and hopefully have a brighter future where Sam and John can communicate on the same level. And if either one runs into problems, they have specifications and testing out there that can help them to get to that art, to take the art and translate it into science. Because both of these guys understand the art, but if they're communicating with somebody outside of their group, it's difficult to communicate the art and the feel, and they don't want to give all the details. So science would allow them to translate that art into a more communicative methodology. Just wrapping up, I went over the background of why this topic. I went over some emulsion basics and applications. I went over the current specifications, went over some of the examples where they fell short, and then started talking about some of the future. But the main question I want to pose to everybody on this is just, where do we go from here, working together to continue to evolve the industry that we all love? All right, that's it.
Thank you, Aaron. That was thanks, Aaron. Appreciate that. That was a great presentation. My personal favorite is the use of the emulsion demolibility and cement mix tests, which seems to be more of a calcium ion sensitivity test, especially on the anionic rapid setting side, than more than anything, which can be problematic if you're working with aggregates other than limestones and stuff like that. So great presentation, really enjoyed it. As of right now, we have one question, and anybody else, if you have any other questions, please feel free to throw them into the questions tab on the banner on the right side of your screen, or just any general comments. Like Aaron said, this is kind of being brought up as a kind of an open-ended synthesis of where we're kind of at as an industry and kind of how we can move forward. And as Aaron said, there's tons of great work that's been done to date on the emulsion residue side, as well as from a mixed design perspective. But how can we make our liquid emulsion specifications better or more suited to the application?
Well, it's just like anything else. Things need to constantly continue to evolve, and we're going to stand on the shoulders of giants. All the work they've already done to take it from where it was to where it is. And I just that was the main point of this whole webinar, is just to pose the question to all of you: how do we work together to continue to evolve?
Absolutely. So I'll start off with a question, and then I see we have a few people with their hands up. So let's go to first question that we had is, in a bid situation, how does a contractor work with the supplier to get the emulsion that's needed? It seems like the supplier would just provide an emulsion to meet the spec.
And that is a huge problem and a huge impetus. So if you don't have a great relationship with your supplier, and they're going to supply you, let's say, a CRS2P, it's cheaper by and large to make it at the bottom end of the residue, bottom end of the viscosity, and I guess top end of the demolibility, just from a materials cost perspective, which I'm sure you all understand. So if you don't have a great relationship, they're best off giving you the bare minimum, right? If they're trying to, from a business perspective, make the most money, they're better off giving you the cheapest material possible, which is where those bands that are so wide can be problematic. Now, you can have the conversation with them and say, this is what we want, but in a bidding situation, that might not necessarily be the path. So where these situations where great relationships aren't formed, the specs become even more problematic. I don't know if you have any other comments, Aaron.
No, I think you covered it there very well. We have another question here. Out west, BWC specs are missing a demulse or breaking time test, leaving it open to slower chemistries. I guess that's just more of a comment there. So that's great.
BWC? Oh, bonded wearing course. Yeah. Okay.
Gotcha.
all the acronyms get super. Yeah, that's for that specific process. It's a huge problem, because these setup, because it whether however far it's evolved, it's ultimately a hot chip seal, and you need to have that break like you would in a chip seal. But a lot of times people make it pretty slow because it can be a difficult to handle material. It's thin, it's got a lot of polymer in it, so it can be a difficult to handle material. So making it slow sort of solves some of that problems, but you end up creating other problems with how it actually performs in the field. And ultimately, that's why we're all in business, is how that process performs in the field and its ability to break and adhere to the surface below it, wick up and adhere to all of the mix and hold that mix together is fundamental to the process. So that reactivity speed is critical. So I would yell at those people if I was you.
One quick note to anyone who has their hands up. Unfortunately, we don't have the capability to unmute you at this point. So if you have a question, can you please put it in the chat box or in the questions panel, and we'll try to answer it there. The next one is talking about a lot of the residue testing moving towards DSR. The question was, are we proposing that every emulsion mill needs a DSR? And Aaron, you can go ahead and answer that, but I don't think that was the intention. I think it's that can be used as a means of doing that, of testing the residue. But Aaron, sorry, go ahead.
I don't know exactly what I don't think they're going to use it necessarily as day-to-day quality control, but it may be worth being something that you do occasionally, like when you're fully certifying a material, maybe once in a while, because we do need to move away from some of these empirical testing to determine the true residue properties, because I think that will help all these treatments evolve over time. But whether you're going to have a DSR tomorrow, I doubt it, but it's probably gonna. But from what I hear, I wasn't around back then when Sharp was introducing the DSR. It was kind of a gradual that people got it, but everybody has one now for that. Yeah, I'm not sure.
Yeah,
I don't think it's going to be a while if it happens, though. I'm sure about that.
I would agree. Another comment and question. First of all, hi, thanks for the great presentation. I'd like to ask if there's a test method to determine, the emulsion curing time that you are aware of, Aaron.
There is systematically with, let's say, micro and sweep tests for chip seal can be used to kind of determine that, but to really just determine the curing time, well, for one thing, you'd have to have various environmental conditions, but not that I'm aware of. If you know of anything, Aaron Walker, that's specific to just curing without it being a system, I don't know. I know that Europe has the breaking index, but that's a whole different thing.
Yeah, no, I would agree with you. I think for certain spray applied materials, there can be the modification to, I believe it's ASTM D711, the no pickup time for traffic paint, that was used a lot for the less tracking type materials.
Yep.
I'm not sure if that's with the question, the way that one is going, but in terms of cured residues as a residue only and not with aggregate, that's how I would answer that. I think there are other dry time tests that are eluding me at the moment, but that's a good question.
Well, because to be fully cured, you have to not have the water that's encapsulated by the asphalt anymore. So that gets to being more complicated, other than just weighing things over and over. It gets to be more complicated to really tell. That's a really interesting question, though. I know there's deep chemistry ways, but there's no way that I know of that asphalt emulsion plants typically would have.
All right, the next one is a general comment. The aggregate and emulsion mixtures and treatments need to be evaluated and specified rather than expecting every emulsion system to perform even without looking at the aggregate once, much less the job progress. As the job progresses, No amount of testing on an emulsion promises performance with a blind aggregate pairing. This includes PG grading. It's only a piece of the puzzle. And I think we would both completely agree with that.
I absolutely agree. My point was, and maybe I didn't make it clearly, is once you have that, we test every aggregate we do for everything, and we would never stop doing that. But once you have that information, I would hope there would be a way to classify that material, and at least hope that if you're having a similar, so you understand your aggregate, if you're buying from another supplier, you could potentially be able to give them some kind of information to give you what you want. And it also ties back to process, like we talk about chip seal and, or not chip seal, cold in place versus cold mix, different behaviors of the material and things like that. I don't know if that really answered the question, but I completely agree with you. The point is more just if you're dealing with a supplier, kind of tying back to the first question, you have to be able to speak in a certain language. And I guess it becomes at that point you just send them your aggregate. But if they're not equipped to do that testing, let's say they typically only do chip seal, and you need them to do a cold mix emulsion for you, they might have the tools and capabilities, but is there a way we can specify it so that they can get there?
Yeah, and just to kind of add to that, I mean, if you look at any microsurfacing emulsion specification, for example, the specifications on the actual emulsion are quite weak. We have to lean heavily on the mix design process to ensure that we are going to have a successful treatment. So absolutely, I think we're completely on the same page there.
Because I think that piece of the puzzle is already fairly well done, at least for micro. Chip seal probably needs some evolution there,
but any other questions? As of right this moment, we don't have any, and it's 2:06, so we're a little bit over. So with that,
I told you I'd go over.
You did as you promised. With that, I just want to thank you, Aaron, for putting on this great webinar. It's been very informative for all of us, and if anything, we'll open up the door to more conversations to be had. So thank you very much, and for everyone who is listening in, thank you for attending, and I hope everyone has a safe and happy holiday season. Thank you.
Thanks for your time, everyone. Appreciate it.